Hello, my name is Orang Vahid. In this webinar, I'll talk about how machine design and product innovation can benefit from system-level modeling. Let's start by looking at the design process. A system-level model of that initial concept can help answer questions such as, would it have the desired motion? Given the input speed, does it have the right output speed? Does it produce a sufficient force? How much torque does it take to drive the system? Once we have answered those questions, we can continue in the design process by adding more details to the model. These details could be adding friction, more realistic mass or inertia estimates, or even specs from the components that we want to use. Now, with this expanded model, additional questions can be asked and answered. Questions such as what type of actuation should be used? How much power would it require? What is the effect of inertial loads on the behavior of the system? How fast with those inertial loads consideration we can run this? And other questions such as the loading applied to different parts of the system, such as bearings. With the system level model that evolves with our design, then we can continue on this iterative design process and add more and more, such as the actual dynamics of the actuation that we are using, or the power supply, or even sensors and controllers. And we can ask questions from the model as what is the dynamic effect of the actuator going to be on the overall behavior of the system. The process of design can benefit from system level modeling in another ways that goes beyond just modeling and simulation, such as parameter studies or design tool creation. Once we have answered these questions, we might hand off the final design to integration, whether it will be integration with the hardware or even put it in a bigger system analysis, such as formal checking versus constraints and requirements in the context of the model-based system engineering. There are a few examples that I've selected here to help demonstrate the concept that I just talked about. The first one is a very simple slider crank as an example of concept evaluation, basic design exploration, and where we can do with it, such as parameter sweep. The next example brings the level of detail up by including CAD components for better estimates on mass and inertia. We'll expand that model to include actuation and power consumption with electric motor and battery models that added to our mechanism. The third example will be an industrial robot where we put even more detail into the model, but also we'll turn the dynamic model into a design tool, an analysis tool for motor sizing and creating reports. Okay, so the first example, as you can see on the screen in MapleSim, is a slider crank. There are two links, and these are parameterized, so we can quickly investigate the effect of different parameter values on the behavior. There's a mass at the end that we want to move, and we want to move this with different speed that we're applying to the crank. That speed is determined by a sinusoidal excitation with a given parameterized frequency. So let's go ahead and run the simulation and see the results. We can see both the animation of the mechanism in action, and also on the plot we'll see how much torque it takes to provide or produce this motion. Adding more fidelity to model may include adding friction. So we add a friction component to the slider. Now the slider, as it goes back and forth, now has to overcome the force of friction. We run the model again, and we will see that we will have the same motion, but now the amount of torque we require to overcome that friction and actuate the model increases. I want to take it further and do a bit of automation here. We do a parameter sweep app, and by loading the model into the app, we'll select a few parameters, such as the mass at the end that we are moving back and forth, the torque, the friction force that we are exerting on the system, and the frequency of the motion. Here we have the changes in the maximum torque required as the function of the friction torque and the mass of the that you're moving. We'll see that for low frequencies of motion, the friction is going to be the most important factor. But as we increase the frequency of the motion, the speed and acceleration, the inertial forces become the dominant factor. The next example, as we talked about, is another slider crank mechanism, but this time it comes to MapleSim as a CAD assembly that is imported into MapleSim. Every component has its density and geometry and mass inertia calculated from it. When we bring these components into MapleSim as groups of different subcomponents, we get 4 rigid bodies with accurate estimation of mass and inertia. We connect them together with joints for rotation and translation. And now we have a model of a slider crank that is a lot more realistic. We expand that model by including a DC permanent magnet motor and actuate that motor or energize that motor by a lithium-ion battery. We also expand these, just similar to what we saw there. We are including friction to the joint because, as an example here, we know the friction for that particular joint. I want to know the effect of it in, for example, how fast the battery is depleted, providing a certain motion. So again, running the simulation will give us the animation of the resulting mechanism in action, and also various quantities that we have plotted, such as the rate of change of the state of charge, or the torque required to run the motor, or the speed or the motion of the slider. We can see that there's a constant value of torque for resisting the friction, but also is a fluctuation that comes from the inertial effects. The faster we move, the more important will be the inertial effect. The third example is a bit more detailed, is an industrial pick-and-place robot. It's a system with 3 links. Links have parameterized mass, geometry, and inertia. Each joint is driven by a motor gearbox component. It also parameterized. The path is provided by a lookup table from measurements or other requirements. The path is converted to joint motion by an inverse kinematic block. Running the system here will give us, similar to the other examples, the animation of the robot in action as it performs a task assigned to it. And system level modeling allows us to make changes to the model and see the effect of it on a variety of different output. And you can see that there's all sort of outputs are created from this model. And so a complex model creates a lot of outputs. So it's important for a designer to not only investigate all of these, be able to create more focused tools to answer specific questions. In this example, we use this dynamic model of a machine, in this case a robot, and we create a design tool from it. The design tool ID is attached to the model, so we'll just open it. Design tool has different segments for running the simulation, doing motor performance analysis. So we start with looking at the simulation results by running the model, similar plots as we have seen from the MapleSim itself. We can group them, add more post-processing, such as looking at the RMS of the signal, the min max. So this quickly can help with focusing on the more important parts of the simulation. Motor performance, having speed and torque plotted together to see what is the envelope of operation of each of the 3 motors in this example, and also using Maple to superimpose the plots of the actual usage versus the electric motor characteristics. Quickly here we see that by doing this type of analysis, we can select a motor, whether a particular motor from a catalog or a manufacturer would fit a particular usage for a particular path and torque and velocity. Similar to what we have seen before, grouping of the results is very important. The user can export the results to Excel, for example, for reporting. Here we export the entire result set for this particular simulation into Excel. Very similar to the first example, but here embedded in a bigger tool. We can do parameter sweep on the mechanism, on the entire mechanism. You can see that the values of parameter are changed and different outputs from the system are investigated to make sure that for the range of design or family of design that we are interested in, all the requirements are met. Few takeaways from this quick webinar. System level modeling gives the ability to the designer to have a virtual representation of the model, which guides him or her through the design process. Parameterized model by themselves are tools, but the designer can expand that to become engineering apps, and those engineering apps bring focus and utility to perform a specific parts of the design, and also enable a wider user base to answer design questions. System level modeling also provides understanding of how the design interacts with a bigger system and how the overall system can be optimized to work perfectly. Thank you very much.